Welcome everyone to But What Exactly is Electronic Design, organized by the Institute Technical Council, IIT Bombay. We are very pleased to have with us today Dr. Mahesh Mehendale. Dr. Mehendale is is a Texas Instruments Fellow, and he leads research in the Kilby lab. Presently, he is focusing on embedding machine learning targets always on Internet of Things sensor nodes. Since joining Texas Instruments in 1986, he has led the development of multiple industry-leading digital and system-on-chip designs and IPs including C27x, C28x DSPs, DM642 digital media processor, hardware accelerator for high-definition video compression, and ultra-low power microcontrollers. Dr. Mehendale holds a B.Tech degree in electrical engineering, M.Tech and Ph.D. degrees in computer science and engineering, all from the Indian Institute of Technology, Bombay, from where he received the Distinguished Alumnus Award in 2012. Mahesh has published more than 50 papers at international conferences or journals and presented many invited talks or tutorials. He holds 19 US patents. He has co-authored a book on VLSI synthesis of DSP kernels and also two book chapters. He was elected senior member of the IEEE in 2000, received the Zinov Award for Thought Leadership in 2014, and was elected Fellow of the Indian National Academy of Engineers in 2016. Over to you, Dr. Mehendale.
All right. Thank you for the introduction and really warm welcome to all of you. It's really great to be talking to IIT Bombay students in the institute where I probably spent about 11 years doing all through my B.Tech to Ph.D. So a lot of fond memories, and what I wanted to do today was to really share with you excitement around electronic design as a career, and specifically the heart of that, the semiconductor electronics, which is really enabling making a better world. So I wanted to start by really showing you a small clip which actually shows what electronic today is being able to do and how it is really touching our lives. And I think post that video, I will take you into some of my reflections, my perspectives on this topic, really based on my 3+ decades in this industry. So I hope you can enjoy this short video. So hope you enjoyed this. Electronics is indeed touching our lives in all these ways, and really semiconductor chips or integrated circuits, as we call it, are really making that happen. Pretty much anything that needs power involves a semiconductor chip for really converting that power, processing the data, and processing the signals. And it's not just what needs power today, but if you see the trend, increasingly what used to be mechanical or electromechanical devices are beginning to turn electronic. So what electronics enables and the power of that, it's just really keep growing, and it is really amazing to be a part of this journey. So the journey hasn't happened recently. It's really more than probably 4 decades where the integrated circuits have been able to really revolutionize electronics and just impacted how we really interact with each other, how we live and play and so on. And the semiconductor chips and the semiconductor technology innovations have been really a key to make that happen. So I have a small set of questions for you, or a question, whether you know what's the significance of these numbers. If you know, you could key in, or let me just give a few minutes if anybody knows why are these numbers significant, or what do they indicate. Of course, we are talking about in the semiconductor context. I'm not sure whether anybody has an idea. All right. Fine. I think in the interest of time, let's... oh, okay. Yeah, I think somebody got it right. It has something to do with IC patent. So, Aaron, okay, good crack. All right, so I think the significance of this is really 9/12 is the date the integrated circuit was invented. I think we all know 9/11 as a date that in some ways changed the world. And 9/12 also has a similar significance, is the invention that changed the world. The other number that was there is really the US patent on integrated circuit that was invented by Jack Kilby. The lab at TI that I work is named after him, and incidentally, the work that he did was in the same campus, not too far from where I sit. So it's really a great inspiration for all of us. As you know, he won the Nobel Prize for Physics in 2000. So the journey that started with the invention of integrated circuit required continued innovations, and those innovations even continue as we go on today. And many of these innovations, as you probably know, have been captured in a famous law, and one of the effects or the result of this semiconductor technology revolution is evident in this graph. This was from a paper presented at ISSCC. This is one of the most premier conference for semiconductor solid-state circuits. And what it is showing, y-axis is a log scale, is to how an average transistor, which is a building block of other electronic circuits, how that has really exponentially been decreasing continuously. This paper was presented in 2003 by none other than Gordon Moore, and that's the Moore's law that you probably have all heard of. So what the Moore's law has really enabled is over generations, the generation happening every 18 to 24 months, being able to shrink the dimensions by 70%, which means the transistor density, number of devices, per unit area doubles, the cost does not go up that much and the chip cost comes down. So that really has been the magic, if you will, of this whole semiconductor technology. And this journey is not easy, but has required a lot of innovations, and that has really enabled this technology revolution, which shows the graph that I showed earlier. And this journey, in some sense, continues. It's not just about the cost, it's about performance, it's about power, and there are so many things that electronics is really enabling based on this kind of a revolution. As you know, there are really endless applications where semiconductors are feeding in, from personal electronics, smart home, industrial and automotive, and we could go on and on with this list. And being able to be part of this journey in some sense has been the exciting part. If I were to just go back onto chart, what it is really showing is this area around here in 1985-86, where the semiconductor electronics started really move from earlier bipolar and NMOS, PMOS to a CMOS kind of a digital implementation. And that's really around the time where I started my career at TI or in this field, and having witnessed this journey, riding this journey in some sense has been a great experience and an excitement for me. All right, one other thing that strikes me when I looked at this journey is what this electronics has enabled. And one thing that I always mention is that we actually use computers and computer-aided design to design these chips. And over this entire journey, or even as we go forward, we always seem to use devices which have far less capability, or computers or workstations which have far less capability than the actual chips that we are designing on these machines. And that journey has continued. And I was just thinking about when it all started, and as I mentioned in 86, 87, the engineering workstations on which we were doing chip design. I thought I'll just mention it here in terms of what kind of system configurations were there, and these used to be, at that point, powerful machines that we would work on, and not many available. So here is one of the workstations that we used. This was called an Apollo TN3000. This was later acquired by HP. And just look at that configuration, the main memory, hard disk, and the processor megahertz. I think it's really evident that we have done chips based on these, and through that bootstrapping, if you will, today M's have become giga, and now giga is becoming tera, and so on. But I thought I'll just share this to kind of give you a perspective on this, what this smooth saw, or the semiconductor revolution, has enabled, and from where we were in the workstation today to in 86 or mid 80s to where we are today with what we find inside our smartphones. It's just amazing and mind-boggling. There's another interesting numbers, or actually a date, which is somewhat dear to me, again part of my journey, and interestingly it coincides with today, which is 7/7. And this date was set at 7/7. A funny incident is because, as you know, in the US, we normally talk about month followed by day, and in India we are day or followed by month. And with 7/7, we didn't want any confusion, because it's something that everybody will understand as a day. And this was the day when the first commercial DSP called Ankur was designed in India, and we did what we call as a PG. We released this for manufacturing from India. Some of you may have heard about it. These devices are called C28x DSPs, real-time controllers from TI. And this is something that I was part of a journey that's very close to my heart. And where C2000 family is today, it really has proliferated. It enables real-time control. It's in motor control and drives, and of course automotive and some of the most modern electric vehicles. And also going in areas about digital power and energy delivery. So really just giving you a flavor for what electronics has enabled, and really doing that by reflecting on some of my journey associated here. So going into a little more into what goes into these electronic integrated circuits and so on, and what makes it work. Our world in some sense is analog, and most of these devices are really gathering information from the real world and controlling or giving information or connecting back into the real world, which is analog too. The information is all kinds of different forms of sensing, if you will, and then there are actuations and controls at the output. So any electronic system, if you see, will have analog, some form of analog to digital conversion, being able to process that digital data and convert it back to connect to the real world. That's analog. And in some sense, analog and embedded processing is really what is the heart of making all electronics work. This really shows another view of it, little more detailed view in terms of really how the entire signal chain works, from getting your analog signals through data converters, being able to process them, send it back, and then there are also other electronic capabilities, and I talked earlier about being able to manage the power, and of course there's a communication through wireless connectivity, clocking and timing, feeding that. So an electronic design really requires, or integrated circuit requires building multiple of these different components and different chips, many of them integrated all in a single device and so on, trying to solve different applications, different markets, and many of those things that you are all familiar with, you have seen, and so on. So I got, just give me a minute. So I talked about the Moore's law and the journey so far, and the question really is that where does it take us going forward? As the scaling ended, because now we are down to geometries and thicknesses where we can count them in terms of number of atoms and so on. And in some sense, the journey slowed down in terms of technology scaling, but that more of Moore, as we call the y-axis here, continues. And maybe at some point when you are at 7 nanometer and lower geometries, there may be other things beyond CMOS that may emerge. And this aspect of continued miniaturization is going to be one dimension where the semiconductor electronics and semiconductor technology is going to take us. But the other exciting dimension that is emerged is what is called, or termed as, more than Moore. By the way, this chart comes from a Semiconductor Industry Association roadmap, something that is available online. If somebody is really interested, you can go and study, and there are a lot more details behind this. But what really is happening is this other aspect where in an integrated circuit, you not only want your memory and the digital content, but increasingly your analog contents being able to handle higher levels of voltages and powers, being able to integrate passives, and of course there are sensors and actuators in the whole area of MEMS is pretty exciting. So that aspect of more than more is where there are many opportunities along with more of more. The other interesting dimension also is that instead of taking all these electronics and integrating on monolithically on a single die, that's what we call a system on a chip. There is this trend of instead of doing everything in a single chip, can I do it inside a package? And this package level integration through a system in a package, so system on a package, is another aspect of where this trend is headed, and that allows a heterogeneous integration of multiple technologies that can come together and still be able to get it in the form factor and the cost and the power and the performance that we need, providing this diverse capability from sensing actuations to your analog interfaces to digital processing and memory and so on. So that's where this journey is continuing, and I think that I really don't see this ending anytime soon, and more and more electronification of things is going to happen. That's the excitement of being part of this journey. So since I think the discussion is really about what are the careers opportunities and related to, and what as it relates to electronic design, I thought I'll just put this chart because the whole electronic design ecosystem has really multiple dimensions and multiple aspects of the ecosystem. What I mentioned here so far is really the integrated circuit design. And the semiconductor process technology, the manufacturing fabs. The Moore's law that I talked about is really about, can we continue to do this miniaturization? Can we include this beyond more diversification of integrated analog and RF and passives? And that's an aspect of a semiconductor process technology development and innovations. And that's one area where there are a lot of opportunities, and it's not only the electronics, but material science and other areas that become quite important in that field. The integrated circuit design is really the area of electronic design or chip design, if you will, which leverages the underlying technology and builds the integrated circuit, which feed into the electronic systems. And these are the end devices from your smartphones and the wearables to some of the electronics that we see in the cars for the advanced navigation and so on, and industrial automation. There are many areas, your health and fitness and so on. And those are the electronic systems that build on top of these integrated circuits, connecting many of them and really building embedded software to realize your end system functionality. So there is this whole area of embedded system design or electronic system design, which is also really important. So this whole ecosystem of, I have a very compelling semiconductor process technology. You have designing very differentiated chips, and using those chips, the building electronic systems is really the aspect of a overall ecosystem. And as an electronic design career, you could look at any of these or transcend across and so on, depending the area that catch your fascination, catch your interest. I think there are two other fields which are really allied to this, which is given the complexity of these devices that we build. Some of these recent modern circuits will have billions of transistors, and you can't really place them without having a very powerful design automation capability. So EDA or CAD for electronics, as you would have heard, is an really important part of that. And in fact, when I started my career in Texas Instruments in India, we were designing, really doing this CAD tool development for use by the IC designers, and then I moved into the IC design aspects of things. But electronic design automation is again a very important enabling field by its own, pretty challenging and exciting and area that forms of the overall ecosystem, if you will. And as you go into the electronic system design, since it has embedded processors, they have microcontrollers and DSPs and so on. Embedded software development is important, as I mentioned, and then you need tools. These are compilers, there are simulators and emulators and so on, so that you could develop and debug your software, embedded software. So this is another area that forms your overall electronic ecosystem, electronic design ecosystem. So it's not just only chip design. There are really many aspects of this, and if you look at wanting to do research, wanting to do work for a company, or have your own startup, I think there are opportunities in all these areas, and more innovations are needed as newer challenges are coming, and the opportunities to provide differentiated solutions. So just continuing on this vector, one of the things that I also wanted to highlight is that anytime you are in a high-tech industry like this, in terms of the roles that you can play or your career opportunities, one is the various areas in terms of chip design, embedded systems, technology, CAD, and so on that I talked about. But going to the next level, or the other dimension to that, is what kind of roles do you get to play? And if you want to, I talked about devices that have billions of transistors, fabs that take probably billions of dollars to set up. Some of these products, the teams are probably 40, 50, or even 100 people teams, and so on. So if you really look at building some of these products and enabling this, it requires a need for roles that drive leadership on all these vectors. This innovation in terms of really driving technical leadership, having deep domain expertise. There is an aspect of execution, time to market, being able to meet some of your requirements in terms of power and performance as per what the goal is, and so on. So there is a very important component of being able to execute and deliver on the products through project program and design management. And then there is an overall strategy aspect of business and product management. And again, depending on what takes your fancy, what excites you, where your passion is, you could in this field go along any of these or a combination of these dimensions or vectors. It's something where there is opportunity for each of these. What products we define, how do we position, how do we identify markets, where the new opportunities are, what key differentiation is required is part of this product management, the overall strategy. Innovation is really core in terms of really having the deep domain expertise and being able to come up with new solutions to be able to provide this power, performance, cost kind of a benefits, and again differentiated features. And execution is an important aspect of this to really make these things happen and translate products that are then delivered into systems and really reach the end customers. I'm kind of wrapping up my talk part of this session, so start thinking about your questions if you don't already have it. But I have been working with for more than 3 decades, I've had the opportunity to interact with a lot of young engineers who come to TI. I also regularly work with many interns, interact with universities and so on. And there are some few questions in some of my discussions have come up and often come up. And I thought I'll kind of share my thoughts on that. I think one of this is that, hey, why are you working for a company? Haven't you thought of starting your own? And when I talked about this entire electronic ecosystem and need for innovation, of course, that's really a very important field for really startups and entrepreneurship. And there are many, many examples in each of those domains that you can see where a startup has really come in, bring in innovation and made a huge difference and made them big. So I think that opportunity exists. For me, it has really been the excitement of working in the forefront of the technology, and the kind of freedom that you could get inside a company can still give you what I would say is this aspect of intrapreneurship. So this is a book mentioned here that I came across many years ago, and I was reading it. Some of the concepts there really appealed to me, so I thought I will just mention it. And these 10 commandments are something that I picked from there. These are something that have in many ways been the guiding principles, if you will, in terms of how I have seen not just for myself but many of the successful technologists in the field who are still working in the big company context in the research labs of these or even in the development. There is a need and a room for innovation, and this concept of entrepreneurship is something that is probably can give you maybe best of having to leverage the opportunity of working in a bigger company, but really still having freedom and the excitement and the entrepreneurial aspects of being able to innovate and build new things. So again, it's something that I thought I will share with you. I'm not going to walk through these commandments, but I think again, anybody can maybe Google this if you want to know more about this book and some of the thoughts here. Definitely a read and a lot of things here that resonate with me pretty strongly. I guess finally the question again that comes and I've been asked multiple times is that how come 30 years, same field, same company, and so on, and how do you really decide on your career path and so on? And I just wanted to share with you how I see this. I think everybody has a maybe different thoughts and perspective, but this is something that I have seen work for many, work for myself in terms of how do we really decide on a career path. Our technology field is evolving so rapidly that one of the things which is constant is learning. And unless you keep learning, unless you are acquiring new skills, new capabilities, I think that's really essential to be part of on this career. So essentially, at any point in my career, I've always asked these three questions. Okay, I have certain experience and expertise, and am I able to really utilize it in the work that I'm doing? And is it making a difference? Is it making an impact to the business? Am I being able to build products that we are able to sell and make the world better, as I mentioned? And that continues to be the driver. And equally important with that is that am I developing new skills? As I mentioned, in our this field, the technology is moving so rapidly that you need to be learning all the time. And I think I must say that my IIT education really equipped me to be able to do that aspect of continuous learning. And even today, I would say I continue to learn, and I'm a student in some way in heart. But this aspect of are you able to, do you get space and are you able to spend time to really sharpening your skills, building new skills, strengthening your expertise is an important aspect of your really job and work, and that's the other question that I always ask. And finally, something which is very most important to me is that am I having fun? Am I really enjoying what I'm doing? You get up in the morning and do you look forward to taking on this new challenge, solving something exciting, thinking of some cool new ideas and so on? And do you have the team that you work with, the environment, and really the mind space that gives you that that enjoyment in some sense, and that enables your drive and passion? So anytime in my career, I have seen things not working on any of these vectors, I have done something about it. And so it turns out that TI gave me the opportunity to be able to really address and move and work along these vectors. And so this is something that I shared with many and with many of my industry or even other friends, and they all kind of resonated, saying that, yeah, I think this is something that are really the vectors that can really keep us going. So I thought I'll use this opportunity to share some of these perspectives, and with that, pretty much pause and take your questions. I hope we have time. Almost. Oh yeah, we have time.
Okay, sir. So, Sahasrajit is still having a bit of network issues, so Adesh and I will moderate the question and answer session. So,
Okay.
one of the questions we have is, what do you think is the best way for students and hobbyists to make up for, so to speak, the hands-on experience that they might miss out on because of being unable to access resources an institute provides due to current work-from-home situations?
Oh, sorry, can you repeat? I think I kind of didn't hear the whole thing. You said work from home. Is last part I heard the challenge, but what was the question? Sorry.
Yeah.
Can you repeat?
So, what do you think is the best way for students and hobbyists to make up for the hands-on experience that they might miss out on because of being unable to access the resources an institute provides because of the current work-from-home situation?
Okay. Yeah, I think some sense a good question. I think I will have two comments. I think the first is that what we are going through is an unprecedented situation, and it's probably already 3-4 months, and we don't know how long it's going to last. But in a bigger scheme of things, this is not like a huge period that if you don't really have access to things that you are going to be stalled. So my take right now is that virtually you can really learn the many things. There are tools, simulators, and so on which you could try things out. Many of the cases for many of these embedded processors and so on, there are kits like Raspberry Pi and Arduino and the launch pads for some of the TI DSPs that are available. And if you ask me how we are working today in this kind of an environment, is really around that. It's virtually you can collaborate. There are online learnings possible, and if required, we can get these boards. We can have them at our desk and be able to play with it, learn. So I would say this is not a situation that's going to be permanent. And given where we are today, I think there are many tools and online forums and opportunities where you can really continue to learn, develop your skills, develop some interesting ideas and test things out and so on. So I think that's how I see this.
All right, sir. I hope you can hear me.
Yes, I can. Thanks.
So then there is another question by Puneet Jain. He's asking, what are your views on freelancing as an electronic system design engineer, be it system design, PCB design, schematic design, etc.?
Yeah, so again, I think there are multiple models, if you will, that you could employ. You could work for a company, have a startup, or just be on your own, being able to really do some of these work. I think it's something that is possible, but my sense is that typically the products that we develop, maybe the end electronic systems or chips and so on, are so complex that typically it's not a one-person job. It's a team sport, as I call it. So yes, you need deep domain expertise, and you could be a very strong system design engineer with picking some of the fields that you talked about, but that you would require to be working in a bigger team context. So yes, you can freelance, but I think a better model would be to have a small freelancing team, if you will, through which you can actually develop and offer services for doing complete system design, or maybe have your own ideas of systems that you want to build.
I hope that answers Puneet's question. Then we have Roshni. Roshni, you can go ahead and ask your question.
So, what is the work environment in Texas Instruments like? Do you work on your own ideas, or do you try and develop designs as per specifications set by a customer or someone else?
Okay, so yeah, so TI is a product development company in the sense, right? We make integrated circuits. So in terms of what we do, we have multiple businesses inside TI, and I talked about this analog and embedded processing. And each of these businesses address multiple dimensions and aspects of the market. And we have architects and product development managers and so on, who understand what the customer requirements are, what the application's emerging needs are, and based on that define what the products that need to be. So the specifications of these new products are influenced by what the customers need, but they are something that really are developed by including your own ideas, your own innovations that will provide something unique. You need to be able to offer customers something that is compelling, that addresses their needs, and it's something that is unique relative to your competition, and that requires deeper understanding of those customer needs, defining the right product spec and an underlying technical innovation. I think, and that's the teamwork or the thing that I was talking about, and we need all of these. So I think that's an aspect. So if you have your ideas, and if you are in this field working on a specific problem, of course you will have ideas, and you can develop them, make them part of the products that you are developing, and then the intellectual property that you generate, you could protect or do it through patents as one avenue. So the work environment in TI is something that is really, to me, a great place from being able to really pursue your passion. There are a lot of technical challenges that we need to solve, and we do get the space and freedom to do that. So the way I have perceived TI is a place where you get to work with at a worldwide level some of the best minds and the best people in this field. We call what ourselves an open door policy, as in you can really walk into anybody's office or reach out to somebody. These days you can't walk into offices reach out to somebody and really be able to discuss areas, learn from each other, and then the whole purpose of what we are trying to do is to build differentiated product that needs innovation. So innovation is a necessity for what we do, and hence being able to have your ideas, being able to persevere and build them, translate them into product is something that we do not just in the research lab, but even in the development R&D places where we are doing design. There is a need and a scope and opportunity for innovation, balance with the strategy and execution that I talked about. Okay?
Yes, sir. I mean, there is a follow-up, there's a sort of a follow-up question by Shiva. So, the question is, how does work differ in TI India as compared to the TI headquarters? Is the work in India, in the Indian office, equally cutting edge?
Very good question. So I was part of, I presently in Dallas in Kilby Labs, but I was in TI India for 30 plus years, and a lot of the work that I talked about, Ankur and digital media processors and many of those things were actually done by the teams in India. So at a global level, outside US, India is one of our leading, the biggest R&D site, if you will, and in terms of chip design, both analog and embedded processing, some of the top key leadership products in the industry, they have all come and developed out of India. So I think the simple answer is absolutely yes. The work that we do in India is cutting edge and is really leadership. And I think look at it in two ways. Therefore, if TI is building a certain product, every product that we build has to be really world class to be able to invest and differentiate and being able to really excel and win the markets that we are targeting. That requires world class solutions and best in class solutions. And the whole ecosystem requires you to be really doing that kind of work. So I think the simple answer is absolutely the work that we do in India is as good as cutting edge. There are many innovations, many products which have been conceived and designed in India, and so are in other parts of TI world. So I would say that, yeah, I think it has been really a great place to be in India and being able to work on these leadership products and technologies, and that is something that has always been an excitement for me. So, okay.
All right. That answers the question very well, sir. Then we have another question from Anand. Today, there are many machine learning accelerators which are developed by university level research groups. How many of these reach as a product to the customer, and how do industry experts decide if some claimed gain is worth exploring?
Sorry, what is the last point? What is worth exploring?
How do industry experts decide if some claimed gain is worth exploring?
Okay. So, yeah, I think there's so much excitement around machine learning accelerators, and I agree there are not just the universities working on it, there are probably 400 or 500 startups doing various aspects of machine learning and so on. So there is a huge amount of excitement around it, and for a company, it's really a question of what problem we are trying to solve, what machine learning solution that is required. Do we have technology in-house and the expertise with which we can build it? And in many cases, it is really leveraging what's being done out there. For example, at TI, and so do many companies, we fund research at universities. You may have heard about Semiconductor Research Consortium, where many semiconductor companies, they come together and fund research at universities. And one research area where there is a heavy amount of funding is happening is AI hardware. And that's the space where we get to work closely with the universities and try to understand, explore some of the high-risk innovative challenges. And based on that, you design a machine learning accelerator that meets your needs and your product. So yes, a lot of these things are happening, and you do actually leverage that. I think while machine learning by itself is a relatively a new area, it is not. And understanding what is claim versus what is reality is an aspect that all companies or we all have been doing. So I think machine learning in some sense is no different. You see papers which have all kinds of claims, and once you go a little deeper, you can really understand what the claims are they worth exploring, and what are they meeting the requirements that our product is asking. One simple technique that I use and I've seen very successfully being deployed is that engineering is all about trade-offs. If suppose somebody comes and tells us, hey, here is something that is 10x lower power than anything else, any other machine learning accelerator, right? I think instead of saying, wow, this is great, which it could be, there could be some real cool innovation there. I think the question that you need to ask is that, okay, so what is it that you have given up, right? And that trade-off and understanding that trade-off is at the heart of really deciding whether we pursue that particular innovation and adopt that, or it's something that we understand what the trade-offs are and decide in our product context not to make those trade-offs. If I talk about the power thing, there are many techniques that you would see where you can get aggressive power reduction, but that will come at the expense of accuracy. And is that accuracy trade-off acceptable in a machine learning context, or detection rates and so on? Many times some of these power things will come at the expense of area and cost, and can you afford that, and so on. So there are those trade-offs, and understanding those trade-offs are really at the heart of that question of how do we evaluate and decide if a particular gain that is claimed is worth exploring. So if you are really developing something interesting and you want to put out and claim where I think if you share these trade-offs underneath and an intuitive perspective of what has enabled you to get those gains, then that would make your innovation, your technology more acceptable, and the industry will adopt it. Okay.
Okay. We have a question from Reet. He asks, how will a first-year student who has just started learning about the world of electronics explore or pursue something in the domain of electronic design?
All right. So I think there are different ways of doing it. Some of it is really individual passion, and I have seen even some of the 12th standard students who are doing very exciting things with robotics, and you probably may have done things yourself and actually tried building your own cool some electronic systems using some of these boards I mentioned, right? Arduino and Raspberry Pi and so on. So I think there are 2 or 3 aspects of it. If you have some interest and passion these days, many of these are accessible. You probably can join some club that is building an autonomous car or something at IIT and pursue that. So there is this aspect of I am passionate about this, and can I just find the avenues and explore and develop them. The second part really is about building the foundation or fundamentals, because I think one is to be able to use these designs and being able to build interesting electronics, but really being able to understand the fundamentals that go in building all these electronic systems that are really important. So as a first year, you have at least 4 more years of undergraduate and maybe more beyond. While you can really explore and be excited about these passions, I would not really lose sight of really building the foundations, the fundamentals of really starting with maths and physics into the core of signal processing aspects of things and the circuits things and so on. And I think those are the foundations. I think after so many years, the partial differential equations have remained the same, and so is Kirchhoff's law, and Ohm's law for that matter. So I think building those fundamentals, learning how to learn is another skill that I think is very important to develop. I think that's what I would recommend. That would be my suggestion.
Okay, so we are running rather short of time. I'll be clubbing a couple of questions here and ask them as one.
Sure.
Okay. The question basically is, there are very new techniques generally related to FPGA implementation for. So the question basically asks, what are your views on FPGA market for deep learning and AI, and chip design for Bitcoin mining, blockchain applications? And there are these novel areas, and what do you think is the new novel area, a new area that's coming up?
Okay, so I think a lot of interesting questions. I'll try to keep it short because we are kind of running out of time here. So FPGAs have a space clearly in the electronic system design. Any idea, any concept, if you want to really build it pretty quickly, FPGAs will allow you that programmability, that flexibility. What the processors do with software programmability, FPGAs do with hardware programmability. So there are FPGA solutions even targeting deep learning and AI, and those of you follow some of the products, Xilinx has acquired some of the machine learning companies, and they have a big push where they offer solutions and embedded cores to be able to do deep learning and AI. So I think that space is pretty much very much an exciting space and an opportunity there. When you talk about an FPGA market, there are two things. Are you building a new FPGA or are you building an electronic system using an FPGA? My comment was on the latter. Building a new FPGA is also possible. I mean, Xilinx and Altera and some of these guys, they keep coming up with newer designs. And again, in that area, a lot of innovation happening in terms of new architectures for FPGAs. So that's another aspect which is also interesting or exciting. What are the new areas? There, security is a big area. There we have seen accelerators for Bitcoin and so on. So there are many areas that are emerging where an highly, I would say, power efficient, low cost, high performance solution enabling that is really key and important. I think this whole space of electric vehicles and autonomous vehicles, we see autonomous cars today, but I think there's a lot more to be done there. And that's an area that is ripe for innovation. The other big area that I would point out is really healthcare, the aspect of early diagnostics, that is with AI, without AI. And this whole, there is this new field of electronic medicine and drugless discovery and so on. So I think this whole area of healthcare is another opportunity where multiple things are happening. I don't think machine learning by itself is done. There's going to be, I think, more areas there that are going to be explored, and the machine learning underlying architectures and paradigms are getting more and more brain inspired with some of the new ideas emerging are also areas near term to look at. Those who are trying to do things in machine learning, there are these convolutional networks and spiking networks, and then there is recently a lot of work happening around this area called hyperdimensional computing. So I think keep looking. I highly recommend following what's being published in some of the recent conferences. The area that you are excited about, find a conference or find top 2 or 3 conferences. I mentioned ISSCC, Solid State Circuits Conference. For if you are into CAD, there is a Design Automation Conference, there is VLSI Symposium. I pick some of the key conferences, look at IEEE recent publications, and that would give you very good ideas and insights into where some of the new things that are evolving. All right, I think we are over our time.
Yes, sir. If you don't mind, can we take up one last question?
Okay, sure, I can do.
Then we'll end it after this. All right.
Yeah.
So,
Okay.
Sahasrajit was asking, how is your shift from PhD in computer science to industry experience in electronic device like? Could you elaborate a little?
Yeah, it's been a very interesting journey. I did my BTech in electrical engineering, and I at IIT Bombay, and I was doing masters in computer science. And as part of my master's thesis, I worked in this area called silicon compiler. Essentially, it's electronic design automation or a CAD tool for doing chip design of a certain type. And that got me fascinated about this, or excited about this whole field of VLSI. And at that time, there were not many opportunities in India, but Texas Instruments decided to open its R&D center focused on CAD, and that's how I started this. So after my master's, I joined TI. There was always a desire to pursue research. So almost 7-8 years after my working, I decided to come back to IIT and pursue my PhD. PhD was in computer science and engineering, and my work was more on the computer engineering side. There are a lot of aspects of electronic design, especially the chip design, has a very strong computer science, computer engineering foundation that is required. Specifically, I worked on these aspects of hardware acceleration for many of the digital signal processing, building blocks, matrix multiplications, FFTs, DCTs, and these transforms, and so on. And I think that my work at TI and my PhD work has always transcended between computer engineering and the electronics side of it, and chip design and chip architecture area that I work on. They require both those fields. So it's something that has been really synergistic, and something that I've been able to really heavily leverage and has been really great enabler into the various vectors that I have explored. What is interesting is that when I started working on machine learning, and you look at convolutional neural networks, the underlying compute engine there, convolution, is matrix multiplication, or if I just want to put it simply, it's a weighted sum computation. So what's interesting is that many of those vectors that I explored as part of my PhD, and even after my PhD, I used to work with some other master's students or interns exploring some of those vectors. Many of those have now suddenly still very relevant, and I'm able to leverage some of those ideas into the area that I'm exploring now. So yeah, it has been very synergistic, something that I can leverage, and has been a great experience.
Okay, thank you, sir. I sincerely apologize for overshooting the designated time to you and to the audience. This was a great talk. I thank you for coming and sharing so much of your knowledge and experience with us. And I thank all of the attendees for such great questions. Unfortunately, we couldn't answer all of them. Uh, okay, so we'll be ending it over here. Thank you, everyone.
All right. Thank you, everyone. I had really enjoyed talking to you, and just seeing some of the chat questions. Yeah, would have loved to spend more time, but I think hopefully there may be other opportunities. And we all the very best, and hope you see the excitement around this whole area of semiconductor electronics and electronic design. And there are great opportunities and great challenges ahead. So make the best of the best learning that you are getting, and I think this field is waiting for more bright engineers. Thank you.